Hello and welcome to British Academy. We are back to our beloved graphs, and today we will dive into depth first search. So just to remind you, on the previous video we had Python code that actually generates a nice graph like this, and we will be using this graph for our depth first search. So pretty much what exactly is this depth first search? Well, depth first search is a standard, probably one of the two standard algorithms, at least this is how I call them, for searching in a graph. And in our case, we would be starting from the point A and we will be finishing in point B, and we will be searching in depth. This means that we would be applying last in, first out principle. So this means that we would be starting at A, we would be seeing what are our neighbors, and the last one that gets into, so to say, our vision would be the first one to be out. So in this case, probably B would be the last one. So after B is pretty much taken into account, we would see what are the next neighbors that we got, and then we would have E, and we will be having at this point E, C, and D, and as E is the last one, it will be the first out. So then we will be having F, and then we'll be having P, and this is everything that you should probably know so far about depth first search. About complexity, well, time complexity, it's big O of V plus E, where V is the number of vertices and E is the number of edges. So it can visit all nodes and edges just once. Space complexity, in the worst case, O of V, O of the vertex is to one single path. And it is probably best for scenarios that require visiting every node, such as topological sorting, detecting cycles in a graph, or solving puzzles with only one solution. So far so good. Let's take a look at what we can do. Our graph data is this one, as you remember from the previous video. This is the number of edges, this is the number of nodes. AB1 means that from A to B there is our road, and it's with a value of 1. For this video we wouldn't take care about the values, we would just take into account that a road exists and it is 1. Okay, a road exists and we don't know how much it is, but it is pretty much here, so we care about it. So these are all the edges, and then we have the nodes. So A50, it means here that the heuristics from here to here is 50. We wouldn't care about heuristics, but it is present, so take it as additional information, because sometimes graphs, they have this kind of stuff, and it's good to have a lot of things on the picture when you are working with these graphs later. It would be useful. And then at the end we get A and P like this. And as you can see yourself, actually there is a road from A to P, but later if we change from A to X, there is no road from A to X, and it should be returning false. Okay, so far so good. Let's start with the DFC. Starting from a completely fresh Jupyter notebook, we will be starting with the file name. We wouldn't be using the fancy libraries that we used the last time, and the file name is graph data text. As simple as this. Or let's do it with 2, doesn't matter. I just like it this way better. And then with open file name for reading as file big data string is file.read. Let's see big data string, what is it? Okay, these spaces n are obviously new lines, and you remember here it was 1921 and ending on A and P. So we are able to read it We can even do something like the length, 243 characters. Great, we're doing quite fine. And now let's try to do it. Okay, so first let's see the lines. The lines are raw data strip, if you remember, and then split by the new lines. Okay, here I'm using that one. I'm obviously having some kind of stuff. Okay, I will be using this as raw data, so it's everything is okay. And lines are already put into some nice list. And if we say lines 0, we'll get 1921. If we say 1-0 split, we'll get it like this. And if we want to say to take the 19, we will get it as a string. But if we make it an integer, it would become an integer. Yeah, so we'll say. And first thing is the edges, so it will be like this. And then I'm going to copy this and say edge lines, and it would be, let's say, lines from 1 to, let's say, 1 to 10, just to see what it is. Edge lines, you see, 1 to 10, this is it. What if it was 1 to 15, 1 to 20, 1 to 22? Yeah, okay, so I need it up to somewhere here. And you obviously see that we are missing the first two numbers. This one, this happens because we said that we only need from 1. And as far as we want to make it somehow variable, we say that it should be 1 plus number of edges. And we're perfect. Is it like this? D2, D3 to be the last one. Let's see. Yes, D2, D3 is the last one. We read it correctly. Okay, edge lines. Then what else do we have? Start and end. For start and end, we can say, for example, lines -1, let's see, and this is the start and the end. And in our case, it would be lines -1 split. And if we do not say split by what, for example, by space, it splits by all the spaces that are available there, which is great. Start is A, end is B. Quite fair, I would say. So now let's build our graph. And the graph is a dictionary. And let's try to loop through. So just to remember, what do we have as edge lines? We have these 3 values. Do we need the weight? No, because in this algorithm, in this implementation, we wouldn't need the weight. So let's try to get the other stuff, pretty much A and B. So for line in edge lines, we can say I'm asking for U, which is going to be A, B, and so on, B. And then I'm asking for something I don't care about, so it's an underscore. And this would be line.split. And we do it correctly. Let's see, we get the U the last one, V the last one, and we need to save this UV information somewhere. So let's add it. So if you not in graph U equals this. Let's put the same for V. Yeah, fair enough. And of course, we are going to append here this one. Then it's not very needed, but not needed at all, I would say. Yeah. let's remove it. The idea is that, let me show you what we did. Whenever we find an edge between these two, we are adding this one, and as this one is added, this one is its child automatically. And no need to add this one as well if it is not appearing. Yeah, and now let's see what do we get in the graph. We get a lot of nice information. Yeah, so for A we get B, C, D, B, C, D twice. I think I have run this twice, so that's why I get it like that. Yeah, exactly. Let's see what would have happened if we had added as well the V, as I have done it initially. Yeah. Okay. Nothing fancy. We just need the P and the D3. Do we need P and D3? Let's think. I would say P and D3 are actually somehow useful, so I'm going to leave them. Yeah. They bring some information, although they don't have anything as kids or children. They still bring some information to us, and it's good to have them. Yeah. So they are there. This is my implementation. Then we continue with the algorithm, and we add a stack. In our case, the stack would be simply a list. And in the stack, we would be having the start. So if we say like this, hey, stack, give me the first one, it gives the start. We can say stack.pop, and it will be giving A. And the second time it's an empty list. Yeah. So let's not pop it out. Yes, and then we have something called visited, and it's gonna be a set. Just remember what is a set. A set is a list that only contains unique items. For example, you see we have given A and B, and it returned us A and B only, and it didn't return us this third one. If we make it unique, it returns it, and if we have two, it doesn't return it. Okay, so far so good. We have the set, and now let's do the loop. We are doing iterative implementation, which would mean that everything would be tracked down, and we are not going to use recursion because I don't want to. Okay, so while stack, obviously we broke it because it's an endless loop. Fortunately, we can interrupt. If we say stack pop, we can only enter once. Print stack, for example. Yeah, it works like this. Okay, so while stack node is stack.pop, and I'm just having like this. Okay, the node is A, and what do we do with this A? First, we make a check if node is the end. Just remembering end was P, and the node is A. If node is the end, return true. And this is really absolutely minimal implementation of DFS. And if node not in visited was the set that is visited, then add it to the visited. As simple as this one. And then pretty much say stack extend graph get okay, this is too complicated what I want to write, so it's gonna be something like this. And then that. This one pretty much reverses the list and it gives you the reversed node, which is something, but I don't like this implementation. Let me think about something better. And the something better would be just commenting this one. Would be more understanding, so we'll be using neighbors, and here we'll say graph get node or an empty list. I'll just make it like this, so it is visible. The idea is that this thing, the whole thing, should be actually in a function, so the return true is useful, but the neighbors are kind of a list. Let's see what we can do with them. Do we have the graph? Let's see. And neighbors for the A should be these ones. Yeah, B, C, and D. Great. And what about D? For D, the neighbors should be these ones. Okay, so I hope you understand what neighbors is. Then what we can do is we can reverse them like this for neighbor in reversed neighbors. Let me show you what reversed does. Yeah, it just reverses it. It was the other way around. Let me show you. So it was I and D, and now it is D and I. Yeah, so just showing for neighbors in reverse neighbors. The idea is that we have LIFO here and we just append it. Okay, if node not visited, I don't know what it is complaining for. The tabs are okay. I see here. Something like this. Yeah. Okay. Now, can we run it, or should we make a whole function out of it before? Let's try. Let's try with the whole function. Now, def DFS minimal, and we are passing here the raw data. Okay, this one goes here. This one goes here. Then we declare the graph in the function. This beautiful loop that we already discussed. Then the stack and the visited. And here those beauties. Okay, I had to have some return. Here, return true. And at the end of the function, If we don't see anything, it's our unhappy case, return false. Okay, expected intended block. Okay, something like this. Yeah, do not copy stuff in Python if you cannot, if you don't like it. I'm just thinking, okay. Okay, and then graph append. That's great. The loop is over, then the stack is okay. The stack is okay here. Yeah. Let's run DFS minimal with raw data. Neighbors is not defined, probably a grammar mistake. Something like for neighbor in neighbors. Yeah. Two. That's great. And let's try to look for Z. AP AZ file save. Yeah, it works. So far so good, we are doing fine. But we have a problem, we have no idea what exactly is happening inside. I mean, it obviously says sometimes true, sometimes false, but this is not enough to convince pretty much anyone that it is working. So we need to have some kind of things that are going to make it more beautiful. I'm going to call this one DFS. Not maximal, but it is going to be with path reconstruction, so to say, and this should be called DFS with, okay, DFS normal. And it's going to be the same at first, but let's try to add something interesting here. For example, printing stuff. Okay, so to say, finding a path from start to end. Yeah. And something that I actually really like is like this in Python times 50, just to show you how it looks. DFS normal already. And why is still false? AP, I didn't save. I saved, but I have not read it a few times more. So now it works. Okay, so we need something called visiting sequence and parents. Okay, I think somewhere here we're going to ask to add visited sequence, and it's going to be a list, and then parents, and it's going to be a dictionary, and the start would have no parents. Too bad for the start. Yeah. And let's also add some kind of steps. It is going to be a counter, and it's going to be none so far. Okay. So if node invisited, I'm just thinking. Somewhere here we should start adding the steps. Okay, step. Okay, plus equals 1. Pretty much what does it do? Step equals 1, and then step plus equals 1, step should be equal to 3. So each time we call this one, it increments by 1 the value. Yeah. So step plus equal 1 is okay to be here. And now let's add it to the visited sequence. Append note. And also we can say, hey, step visiting note. That's actually funny. Okay, so it's obviously we are visiting A, we are visiting B, we are visiting E, F, and obviously somewhere here on, because the if is before, pretty much if node equals n, we didn't enter this printer here. So yeah, we found a way from A, B, E, and F. Let's see whether this is the correct one. A, B, E, F. Yes, this is the correct one. But we want to start from P, and we want to be able to backtrack, and we want to be sure that if we visit more than the lucky case, in this case, everything will be okay. Yeah. So what do? We get some information for the neighbors, and it should be interesting. How do we do it? So for neighbor in reverse neighbors, this one here, somehow if neighbor not in visited sequence, stack.append neighbor. I'm thinking that we were actually lucky so far for not having this one, because actually this thing here is preventing us for getting in a loop, and this is quite okay. And we should have had this one here as well, but so far we don't have it. So if stack append neighbor, that's great. And now additionally, if neighbor not in parents neighbor equals node, and that should be enough, I think. Let's print the nice thing here once more before returning false. Yes, that should be okay, I would say. Just thinking, okay. Yeah. What actually we can do here is pretty much the following. Let's break this one here. You can ask why. I'm not going to answer. The answer is that here we're going to make some kind of information about what we are going to achieve. Yeah, return false or return true. I'm just thinking, yeah, let's keep it like this. Return nothing. or return to, yeah. And now let's find a way to see what we got in the parents. So here we start with if and in visited sequence, pass, else. Here we can say print. Oh, we can say here else return false. Yeah. I would say something like this. And before the return false, yeah, we do not need to get the data if it is false, but let's see here the happy ending print. We're constructing the path to home and a smiley because we managed to find it. So path would be a list, of course, and current would be the end one. Okay, now while current is not none, this is the backtracking path.append current, and current would be equal to the parents of the current. Then of course probably it would be useful to reverse the path.reverse, and print some information about the final path. Final path is something like this. Dot join. I'll use this one so it's divisible what we are doing, and then the path, and then this one, and then that one. Yeah. Append.current is not the way to make it in Python. Yeah. DFS normal. A to P visiting A, visiting B, visiting E, visiting F. Okay. But why didn't we get this information here? That's a good one. And that requires some debugging. I'm just thinking, okay. Visited sequence, obviously end is not in visited sequence. Yeah. Let's do it like this. Yeah, exactly. Great debugging skills. For me, I would say. And this is obviously our final part, A, B, E, F, P. What else can we do? We can make it nice. We can say, for example, total nodes visited, because we have this information. And it could be len visited sequence. And it should be, I guess, like that. Yeah, 5. And what else we can give? Some more fancy information about the path length. And in this case it would be obvious because we are printing it, but it is interesting to hear it. Okay, in this case, total node visited and the path length are the same. Let's take a look here and cut the node between F and P just to see what is going to happen. How do we cut the node between F and P? We find it here in the input, FP. We save to be F to Q. Q doesn't exist, it will exist now. And now let's take a look in our data, testing it. So DFS minimal, it exists, and then the normal. And now it's interesting. Total nodes visiting 9, path length 5, so ACGHP. Is it this one? ACGHP. And before going there, we obviously did some tracking. We did A, B, E, F, Q. We went all the way to Q. We didn't find anything there. Then we got C, G, and H. I would say it's okay. Let's see this one. How does it look like? Yeah. Obviously, somewhere in Q, something happens. Q to P. Q to P doesn't exist. It's from H to P. It's obviously somehow just a bug. Yeah. It should be that Q can be also somewhere here. That's something else. And so far so good. I would say we are rather good with DFS. And let's summarize what we did. We read the file, we made some DFS minimal that actually doesn't make an explicit check whether the neighbors are in the visited sequence. Here I'm using N for neighbor because obviously the word is too complicated and I didn't want to write it many times. Okay, so the DFS normal is like this and it gives us some information. In this case about the total node visited 9, path length 5, which is great, and it also gives us the final path, which is good. So far so good. Thank you for watching Backtracking Academy, and I'll be continuing with the graph traversal and graph search algorithms. Probably the next is going to be breadth-first search, which is going to be pretty much like this with just a few amendments, so it's going to be a really short video. Take care of yourself, have a great day, and goodbye.